3. So before we start the lecture, I want to mention that right now the homework one you can already find on Gradescope, and all the problems you can already finish based on the lecture today. So all the questions will be on chapter 2 about the electrostatics, but except for question 1 is about the vector analysis. And you are required to watch a video also for the last question 5, and that is help us to get some understanding for the math behind the chapter 3. We will use the math in that video to help us solve the problems in chapter 3. So which is what we are going to discuss on next Monday. So today, before I start, I want to mention that in the last lecture, when I calculate the gradient of a scalar function, I really made a detour in the sense that when I calculate the gradient of a function of r, I used the brute force way, right, to calculate the partial x in the Cartesian coordinates, and then sum them together to give us the final result. But that is not quite necessary, and so what's better is that if you directly work in the spherical coordinates, and so if you look at the line element and look at the gradient operator, you can immediately arrive at the conclusion that the gradient of a scalar must be f prime in the r hat direction, and no amplitude in other direction, because f of r is not a function of theta and phi. So if we use the same idea and apply the spherical coordinates in the question 4, when you are dealing with like del dot r or del dot r hat over r square, and if you treat all of these problems in spherical coordinates, and it will be a one-line answer to all the questions. And this is something I want to mention before I start. Okay. So last time we discussed the vector potential, right? And I think we didn't finish the example on calculating the vector potential directly from the electric field. But you can see some of the examples, some of the questions in the homeworks, and so you need to finish them by yourself. And here, let's look at why do we really want to look at the scalar potential instead of the electric field. And the answer might surprise you. So let's see here. For the Maxwell equation, there are two expressions for the electrostatic case. That is, the del cross E must be 0, and del dot E must be equal to the to the density of this charge. And if we apply the first equation to the gradient, because electric field can be written down as the negative gradient of a scalar potential, and if we plug this in for the, we can try to see what's the expression for the scalar potential, and that should give us the del cross gradient of V equals 0. But if you remember from the lecture 1, this we already proved that this is exactly 0. So this is an equation that's automatically satisfied by V. And what's left over is the second equation. So again, we do the same thing. by plugging the del v into the expression for the E, and we arrive at del v equals rho over epsilon naught. And again, we already seen this expression, and we define this del dot del on acting on a scalar to be del square, and this is called a Laplacian. Here, this del square v equals rho over epsilon naught is actually a famous equation called Poisson's equation, and especially there's a special case that on the right hand side becomes zero, and it's called the Laplace equation. In chapter 3, we are going to solve for this Laplace equation, and that will start from Thursday. Now, here let's try to see what's the potential for a point charge. So here, for a point charge, we already figured out what's the electric field, right? That is proportional to 1 over r and pointing along the r hat direction. Now, we can calculate the vector field by simply integrating over this E dot dl, and here we say that we start from the infinity and integrate to the r coordinate, and that simply gives the integration from 1 point to r, and here this point we chose as infinite. And plugging in this E dot dl, which is the E direction must be parallel to the dl because we chose the dl as r hat direction, and that simplifies the expression. And if we do this integral, the result is actually simple. It simply integrates out 1 over r squared, and in the end it gives 1 over r. And because here evaluating 1 over r at infinity is 0, and which means that there's only one term left. So that's the that's the beauty of setting the reference point as infinity to be 0. That actually simplifies the expression of this potential. And now here, because the point charge does not necessarily sit at 0, and if we shift the source position to be r prime, really the potential should be written as q over curly r, where this curly r is the distance vector or the separation vector from this source charge to this point of interest. Now, again, the same superposition principle can be applied to this electric field. So if we looking at the potential of a collection of charge, then we simply sum them together, and that gives the sum. And similar to the electric field, we can change this sum into integration if we really consider a continuous distribution of this charge. And here this is integrating over dq, and this dq can be different depending on volume charge, surface charge, or line charge. And for this for the volume charge, the expression is simply change dq to d tau. Now, now we have 3 different things, right? And we can see that really they can be connected from each other. So in the first lecture, we already know that the Maxwell's equation tell us how to connect the electric field to the rho by taking the by taking this divergence of the electric field gives us the charge density, and the electric field curl is 0. And from the expression of the point charge, we also know that how to calculate the electric field directly from the density of charge, we simply treat this as the integration over all the contribution from a point charge expression. And then to connect from the electric field to this scalar potential, we also know that by definition the electric field is the negative gradient of the scalar potential, and the scalar potential can be obtained by simply integrating this electric field over a specific path, and this path can be arbitrary. And now we also derived that how to go from the charge distribution to the vector potential to the scalar potential, and that is this expression is Poisson's equation, and to go back we simply apply this expression that we get from the slides here. So this completes this triangle, and sometimes you might be asked to calculate one based on the other, and calculate the other from another one, and you will see this kind of question also in the homework. So sometimes using the Gauss law by calculating the electric field directly from the charge distribution might be the easiest way, but that might not necessarily be possible for every scenario. And if that's not possible, you might need to first work out the scalar potential, and then from the scalar potential derive the electric field. And this approach might be able to solve more problems, but it's definitely harder than applying Gauss law in the integral form. And here you can see that this expression is only a single expression comparing to here two expressions. So the Poisson's equation might be easier to solve comparing to the expression for this E field. Okay. Now let's let's try to look at an example. That is to find the potential of a uniformly charged sphere of radius r. So if I draw this so this is the sphere, and it's only a shell, and the radius is r. And to get this potential, we can simply invoke the formulas in this page here. That we can simply get the potential directly integrating over all this charge distribution, and here this separation vector should be defined here. So if we set the origin at the origin of the in the center of this shell, and we are going to look at a specific point on this shell, and this is the r prime coordinate, and now we want to find the potential at an arbitrary point, and because this is an azimuthally symmetric, we can simply choose the point B on the z-axis, and that's without loss of generality, because if it's elsewhere, we can always rotate the coordinate and bring it back to the z-axis. Now, if we do that, then this r coordinate will be z hat. and then this separation vector is simply r minus r prime, and you can see that this should be the separation vector should be this one, and if you invoke the law of cosine, then that directly gives you this r squared plus c squared minus 2rz cosine theta prime, where this theta prime is the angle between this r vector, r prime vector, and the z-axis over here. So now let's plug this separation vector inside this expression, and the integration really is a two-dimensional integral because we only consider a surface charge, and so here is the integration is over d theta d phi, and there is r squared sine theta prime for this surface element. And on the denominator is what we just worked out, the separation vector. And the integration here on the phi direction is really 2 pi. That's what we need to integrate over is the theta direction. That is from 0 to pi. And this integration can be done here. And if we work this out, in the end, you can see that it has two terms. One is r plus c squared, another is and the square root, and another one is r minus c squared and the square root. So you have to pay attention to the second term because here, depending on the point of interest, the r might be larger than z if we are looking at the potential inside of the shell, and r might be smaller than the z. And if that is the case, that we look at the potential outside the shell. So this expression really takes two signs, and it could be an r minus z or z minus r. And if we pay attention and work this out, eventually you get an expression here depending on the sign of r minus z. And in the end, the expression is simple, and but it depends on if you are looking at the potential inside or outside the well. And here we assume that the point of interest or the potential that we are looking at is along the z-axis, right? But that's indeed not necessary. And if we really looking at the r coordinate instead of a z, we should actually modify this z to r, and so this z to r. So what we get is simply replace the z to r, and we get our expression. Okay, so this is the final expression, and to check if it's true, we can simply check the electric field, right? The electric field is the negative gradient of the scalar potential, and what we get is something familiar. It's in this inside. It doesn't depend on the little r here, so inside is 0, and outside you simply take a partial derivative of r, which gives you 1 over r squared. And this expression is what we are familiar with. Like if you do integration, if you do a Gauss integration by using a Gaussian surface that is in the same shape but a different size of this shell, and you immediately arrive this final answer, right? And when we calculate the v, we actually take a detour, and we really go through a lot of math that I'm not interested to show you. But why do you really calculate the potential and the electric field in this way? You might learn from the homework that not all the problems can be solved using the Gaussian surface and the integral form of this Gauss law. So here the homework, one of the related homework is to find the potential of a uniformly charged sphere, and instead of only a shell of the sphere, you need to find out the what's the potential for a sphere that is of solid and with a volume density rho instead of a surface density sigma. But really, what you need to do here is simply do one more step of integration, that is integrate over the radial direction again. Okay, now let's go next. And here we want to discuss, say that we have a surface charge, right? And the problem before is a surface charge. And if you look at this problem, the electric field is discontinuous at the surface, right? So that's not quite trivial, actually. So because here, if we look at microscopically, and on this surface that with a specific surface charge, the E field above, slightly above this surface, can be drastically different from the E field below. And what is exactly this relation between these two? And this is what we want to find out. And to get this, we can simply use the integral form of the Gauss law. That is, here we can design our Gaussian surface in this kind of pillow box, and we should call this as a pill box. Like here, this is of the size can be large, but the height should be really small, and we take the limit of epsilon go to 0. And if we apply the Gauss law to this surface, we see that because here on the edge, the four edges are really of 0 size, and the size is only on the top and the bottom. So the Gauss integral should only go through the top and the bottom, and the volume contains the charge Q total equals sigma times A. So here the Q enclosed should be sigma times A, and the E field should be the E field above minus the E field below. So the E field above minus the E field below should be immediately arrive at 1 over epsilon naught sigma. And this is the only perpendicular direction, right? So to get the electric field along the parallel direction, that is, if we want to get what is the E field here right above the surface and here right below the surface, we can apply the similar idea, but instead of using the Gauss law, we use the Stokes theorem. And for Stokes theorem, we need to choose the closed path instead of closed volume. And we here choosing the closed path is, we can choose a path that runs slightly above and dives down, and then runs back and then dives up. Here the height of this closed path also should be infinitely small, because we are interested in the field right above and right below this surface. And again, this line integral right on the height of this path is 0, because here we really choose an infinitely small height here. And what's left over is again this E integration along this direction, and which is the E above, and then E integrating over the line below, which is E below. And this is we apply that to the Stokes theorem, right? So the integration of this E above and E below over this along this path should be 0, right? So do you know why that should be 0? Like why this integration should be 0? I'll say, so sorry, I couldn't hear. My hearing is not quite good, maybe. So could somebody speak louder? Oh, I will say set up a you reply system next time probably. Okay, so I think that many of you may already know that that is because the del cross E equals 0, right? And if we apply that to the Stokes theorem, the del cross E over any surface equal to the line integral of E dot dl, and because this for any surface that is 0, then if you do that equal to the E dl, which gives you 0 again. And so here, if we apply that, we immediately find out that in the parallel direction, the E field should be exactly the same. So now we figure out the E field right above the surface and below the surface, both in the perpendicular direction and also in the parallel direction, right? So that's all the information for the E field, and we can simply combine them together. And if we combine them together, this means that if we subtract the two E field, that's really along this normal direction, and the factor should be the surface charge over the epsilon naught, just as what we get here. So this is a very powerful expression, and there is also a similar expression for the magnetic field, and I've seen some of the problems simply asking you what's the field right above or below this surface. So if you cannot tell this result immediately, you have to be able to derive them using the Gauss law and the Stokes theorem. Now let's check what should be the scalar potential be doing exactly near the surface. So so first let's take a look at the scalar potential, the value of the scalar potential, and so that means the potential right above the field and right below the field, and that can be obtained by simply integrating over this E field and along the dl, right? But however, the dl is really infinitely small, so which means that because here a b could be plus epsilon n, and a could be simply a minus epsilon n, and this epsilon can be really small, which means this integration it can be 0, and this means that the vector potential must be the scalar potential must be continuous. And however, that's not the end of the story. The gradient of the v is actually not, and that is because the gradient of the v equals the negative e, right? So this is negative e above, and so we simply copy our expression from the E field and add an additional minus sign, and that really gives us a result. So here we are interested, if we look at the n direction, that is the direction normal to the surface, we can express this gradient of v in the partial v partial n. This is by definition, right? And we are not interested in the other terms. There are other terms that's del v dot parallel, but I didn't write here. And now if we simply replace the term here, and what we arrive is this expression, and copying this on the right hand side. And that is because we need to compare both the n hat direction and the n hat direction, and the n perpendicular doesn't contribute to the right hand side, so only the n hat direction is what we are interested in. And so this is the expression along the n hat direction. And this means that if we look at the vector, if we look at the scalar potential, and in the n hat direction, that is perpendicular to this surface, the v itself is continuous, but the gradient of the v is not, or the slope of the v is not continuous. And this is actually something that you will see in the quantum mechanics course. So here we have this Poisson expression. We have the Poisson equation, right? And the Poisson equation has del square Laplacian, and the surface charge can be really expressed as a delta potential. And this is what we have for the v field. Instead of a wave function, we have an expression for the v. But in the quantum mechanics, the minus del square is a kinetic energy operator, and delta x could be a potential. And I think you are going to see this expression. And this minus del square minus delta x is really the Hamiltonian. And you will solve how this Hamiltonian behaves. And in the end, you can see that the wave function is continuous, and the slope of the wave function is not, because of this delta function. And really, that's the same idea here. Now, the next topic that I want to discuss today is about the work and the energy. That is basically to calculate how much energy is stored in our electric field. So we again begin this problem by looking at the point charges. So first we are going to do is to see what's the work that's needed to overcome the electric field to move a charge from one position to another. Then that means that the work should be calculated by doing an integral of force along a specific path, right? And this force is a bit tricky. It's not the force that's it's not the electric field force that we are interested in. It's actually the force that's what we need to overcome the electric field. And so we need to pay attention that there is a minus sign here. And now if we do the integral, and then this simply gives the potential difference. So the work needed from going A to B is simply given by the charge times the potential difference. So now here, let's say that the A point is at infinity. Then this simplifies the expression, right? Only one term left, and that is Q times V. So this means that the potential energy is, or the scalar potential here, is really the potential energy per unit charge, right? So that's the scalar potential is not exactly a potential, and that is what you want to pay attention. Now the next step is how about a collection of point charges? So right now we are not interested in how to bring one charge from one location to the other. Instead, we are trying to do, is to bring many charges far from each other to a position that they sit together. So if they are far apart, then all the particles cannot see each other. So the potential should be 0, and that's the reference point that we want to set. And what's the final configuration is, say this is a Q1 located at R1, and now there is another Q2 located at R2, and the Q3 located at R3. So to solve this problem, we can simply move one charge at a time. And so in the beginning there are no charge, and we bring the first charge to Q1 position. And we don't need to do any work because there are no background electric field yet, right? After we bring the Q1 in place, however, then there will be an E field that's built up by this Q1, and that E field is 1 over curly R squared. And now if we want to bring the second charge in place, then we have to overcome this potential energy, right? And we derived this point charge potential energy before, that is proportional to 1 over curly R. And so here the second charge is still an easy process, and it's proportional to 1 over curly R12. And curly R12 is simply the separation vector between the charge 1 and 2. Now, what happens if we want to bring the third charge in the presence of the first and the second charge? What we need to do is to take care, or we need to try to calculate the electric field of the first one and the second charge, and then we bring in the third one, right? So similar to the W2 term here, there are two terms here. One is for the potential to overcome the Q1, another is the potential to overcome the Q2, which gives two terms here. And this expression can really go on and on, and the expression to bring a fourth one will have 4 terms, and the first term is due to Q1, second term due to Q2, third term due to Q3. Now you really find out a pattern, right? And that's to get all these charges, you really sum them together, and now the total work, if you look at in the first site, might be messy. There are in total 1, 2, 3, 4, 5, 6 terms, right? And this is a long expression, and if we add more and more, there will be a messy term. But you can actually make some observation. So in general, this expression can be written down as a double sum. So whenever we are bringing the ice charge, which is of Qi, we need to take account into all these previous charges, right? So that is what the second sum index is claiming, and then we need to add one by one all of the charges. So this means that this is really a double sum, and the second sum is a conditional sum. However, this expression is still not perfect in the sense that this sum, the second sum, is not easy to do, right? Because that is dependent on this I. And what we want to do is actually simply make the sum twice. So instead of summing up from I goes to summing up j goes to I plus 1 to n, we simply sum j from 1 to n, but skip the I equals to j. And if you look at this expression, in this expression actually sums up the this expression actually sums up this term twice, because we don't really need j larger than I. There is also a portion where j is less than I, right? And these two portions actually are symmetric to each other. And if we count the index from 1 to n, we actually summed up this term twice. And you can try to go over this at home, and if you still haven't figured this out. And in the end, what it gives is that this is a slightly easier sum, and you need to divide by another factor of 2 here. Sorry. So if we reorder this double sum, we can pull this qi out, and this gives a slightly cleaner expression. And if we look at this expression, stare at this long enough, you might actually recognize that this is actually the expression for a potential energy due to all the charges except for the point charge itself. And this is what's actually can be abbreviated as V separation vector of J. And what's in the end is a really simple expression. That is, the charge is actually 1/2 times the work is actually the potential energy is the charge, the ice particles charge times the potential energy it felt due to all the other charges. So this is essentially what you need to calculate the potential energy of all a collection of charges instead of a single one. Now you can think of this as the work needed to assemble all this system together by bringing the charges from infinity to the fixed position. Or you can think of this the reverse way, right? That is to think of what you get by disassembling all these point charges from the fixed position to all at infinity. Now what we want to do next is to continue our line from similar to this what we did to the electric field and the potential energy. We go from a point charge to a continuous charge distribution. And really that's what you need to do is to again rewrite this sum into the integral. And that gives us an extremely simple expression. This is half of rho v integrating over the volume. And also, if you want to do the integration for this surface charge, you need to use, sorry, there shouldn't be a v. So for surface charge, it's sigma. And for this line charge, the density is lambda. Okay, let's take a break now and to see if we can find an alternative expression for this work.